right, here we're looking at section 9.3. So our learning targets for this section are first we're going to identify similar triangles, then we're going to solve some real life problems involving those similar triangles, and we're going to figure out what some geometric means are. So first let's figure out what we know about similar triangles, and continuing what we know about similar triangles is we know things about the angles and we know the side lengths are in a ratio, right? That's just any similar triangle that my angles are the same and that my side lengths are in a common ratio. So we're only going to be dealing with right triangles. So here's my right triangle similarity theorem. So if the altitude, and right altitude is we're going from the right angle to my hypotenuse, which is across from there, and the altitude makes a 90 degrees itself. So if that altitude is drawn, then the two triangles formed, right? So here I have triangle ADC, and I have triangle CDB. Those triangles are similar to each other and to the original triangle. So here I have them drawn out separately. So I've got AD would be considered the long leg. So that part is similar to CD here, because this is the longer leg. And the shorter legs are similar, and the hypotenuses are similar. And so all three of these triangles are then similar. And I know that because I took my right triangle and I drew the altitude from the right angle to the hypotenuse. So that makes all of my triangles similar. So now let's look at this example. Let's identify the similar triangles in this diagram. The first thing I want to do is I want to redraw my triangle so that they all are facing the same way. So first I take this little one, right, and I see I'm going to do the shorter leg going up and down just to keep it all kind of nice and neat. So I've got my SUT, and I know that this was my right angle, and I've got TUR, and this was my right angle, and STR, my right angle. So I want to make sure that my right angles are always in the same place. So now that I've redrawn them, I can say, starting here, so triangle TSU is similar to triangle RTU, which is similar to triangle to RST. And remember that the order of the letters is very important because that tells us the orientation of my triangles. So now here's a couple that I want you to try. You're going to have to tell me which triangles are similar from what you can see. So now here's kind of a real-world problem using those similar triangles. So a roof has a cross-section that's a right triangle, and we can see that here. The diagram shows the approximate dimensions of the cross-section. Find the height, h, of the roof. So the first thing I see is that I've taken my altitude from my right angle to the hypotenuse, and I see I have the lengths of some of these triangles. The first thing I want to do is I want to draw out all of my different triangles, which we get to right here. First I draw out my similar triangles, and then I sketch them, and then I label what I know. And all of these labels came from the parts above that I was told. Okay, and again, I want to make sure all of my right angles are in the same orientation of my triangles, so then I know what I'm dealing with here. So now I can say that triangle XYW is similar to triangle YZW, which is similar to triangle XZY. And I've gone ahead and labeled everything from what was up here. So you'll notice too that this H is in two different places in two of my different triangles. And we could see that just from up here. I can see that H is in this triangle on the left and H is also in this triangle on the right. But in my triangle on the right, it's the long leg, and in my triangle on the left, it's the short leg. So it's in different places, so we have to make sure and label it appropriately. So now that I know that my triangles are similar, I can write my proportions. So I know that the lengths of the sides of triangles are proportional. So I look at YW, right, which is that H, over my ZY, right, which is the length that I know in my big triangle. So I'm really going to be using these two triangles on the sides. So I go my up and down over my up and down equals my XY, so the hypotenuse of the little one, over the hypotenuse of the big one. So you'll see here that I'm dealing with my little triangle and my little triangle, right? That's my little triangle stuff, over the big triangle and the big triangle. So as long as I have that set up, then I know that I've got my proportion set up correctly. So now that I have this, I go ahead and substitute the information from the triangles, and I can cross multiply. So 3.1 times 5.5 and h times 6.3. Then I divide. So I simplify, so I find that h is approximately 2.7. So the height of the roof is 2.7 meters. So I could have done this a different way, right? I could have used this middle triangle and also used the hypotenuse and what I know over here. It doesn't matter as long as I set up the ratios of what I know using similar triangles. So now here you're going to be doing something like we just did, finding the value of x in our similar triangles. So our first step is always to draw out the three separate triangles that we see and orient them correctly so they're all facing the same direction. Then I can see which side lengths are proportional to the other ones. So now we're going to look at geometric means. This was our final learning target for today. So the geometric mean of two positive numbers is the positive number x that satisfies this equation. So I'm going to take one of my numbers in the numerator and the other one in the denominator. So I know that x squared is equal to those two multiplied times themselves, right? And my geometric mean is x. So to find x, I have to take the square root of the two numbers multiplied by each other. So here's our example. Find the geometric mean of 24 and 48. So I know that the definition of my geometric mean is x squared equals ab. So now I plug in what I know. A and b are 24 and 48, so I substitute. And I go ahead and I take the positive square root. When I take the square root of a number, I have the positive or the negative, but here I only care about the positive value. So now I can go ahead and factor. And you'll see all I'm doing is simplifying my radical because I don't want to end up with decimals. I want to end up with my exact values. So I know that 48 is the same thing as 24 times 2. So I factored that out. And now since I see I have two 24s, I can simplify. Since there's two of them, it can come out in front. And I know that this 2 is left by itself, so it stays underneath my radical sign. So my geometric mean of 24 and 48 is 24 times the square root of 2, or approximately 33.9. Generally, we want to live in this exact value unless you're told to find the decimal approximation. So how does this come into play? We're going to be using this when we're looking at these triangles. Okay, so my geometric mean altitude theorem. I've got two geometric mean theorems here, but one is the altitude. So in a right triangle, right here's my right triangle ABC, the altitude from the right angle to the hypotenuse, right, the CD length, divides my hypotenuse into two segments, which are AD and DB. So the length of the altitude is the geometric mean of the lengths of the two segments of the hypotenuse, right? So here's what I'm really looking at. So CD squared. So the length of this altitude squared is equal to AD times BD. Let's go ahead and color these just so we can see what we're looking at. So this squared is equal to my AD, which is part of the line that it crosses and that it intersects, times DB, which is right here. So I see I square this equals these two multiplied. So now let's look at the geometric leg mean with the leg theorem. So in a right triangle, right, I'm still dealing with my right triangle, my altitude cuts my hypotenuse into two segments again. So the length of each leg of the right triangle is the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse that is adjacent to the leg. So that's a lot of words. So now let's look at what it looks like in our picture. So I've got my CB squared, right? So the hypotenuse of one of my smaller ones is squared is equal to DB, so the smaller leg, and the piece that it intersects. Okay, so AB is this whole length right here. So now I can also see that AC, right, is the other hypotenuse that's created in this triangle, is equal to AD times AB. So now I'm just looking at the lengths of the different triangles that I'm dealing with. So now let's go ahead and see this in an example. So I want to find the value of each variable. So I want to here, since I see that I'm looking for the height of my altitude, I want to apply the geometric mean theorem. So I know that my x squared is going to be equal to 6 times 3. So I know that 6 times 3 is 18, so I take the square root of that, and then I see if I can simplify any further, which I can. I know that 18 is divisible by 9, and 9 times 2 gives me 18. Well, I know what the square root of 9 is, so I can go ahead and write my final simplified version there. So the height of this altitude, or my x value, is 3 times the square root of 2. And I want to leave it that way. I don't want to find the decimals yet. So now let's look at B. So here I'm looking at one of the sides of my different triangles, right? The side, the hypotenuse of my small triangle is what I'm really looking at. So now we're going to use the geometric mean leg theorem. So I know that y squared is equal to 2, the little piece, times the whole big piece. So to find the entire big piece, I have to add these two values together. So I end up with y squared equals 2 times 7, which is 14, and then I can take the positive square root of that side, which is 14, and I can't simplify this 14 because it's not divisible by 4 or 9, and I use 4 and 9 because I know what the square root of 4 is, and I know what the square root of 9 is, and this is not divisible by either of those, so I can just say that the value of y is the square root of 14. So definitely make sure you go through these and see which pieces we're using and where we're using them in all these examples. So now let's look at kind of a real-world example. So to find the cost of installing a rock wall in your gym, you need to find the height of the gym wall. You use a cardboard square, right? Here's my square, and I know that a square is 90 degrees, to line up the top and bottom of the gym wall. So then my friend measures the vertical distance, right, from the ground to your eye. So my vertical distance is right here, which is 5 feet from my eye to the floor, and the horizontal distance, how far away from the wall I am. So now I need to approximate the height of the gym wall. So I see here I'm not looking for the altitude here, so I'm going to use my geometric mean altitude theorem because I have the altitude. So I know that 8.5 is the geometric mean of W and 5. Right? So since I have my altitude, I can go ahead and use that theorem, and I just substitute the different values that I know. So I know that 8.5 squared is the geometric mean, so I square that, of W times 5. So now I go ahead and I square 8.5 and I simplify. So now that I just am solving for W, I can go ahead and divide each side by 5. So the height of the wall is not just this 14.45, right? This just tells me what W is. So to find the entire height of the wall, I have to add this W plus 5. So I figure out the entire wall is 19.45 feet. Now many of you stop and say, oh, well, here's my answer, 14.45. We have to stop and go back and see, what am I being asked to find? So in this problem, I'm being asked to find the height of the wall, not just this piece. So I have to make sure and I find the entire thing that it's asking. So I can just add 5 to what I found for W to find my final answer. So now here's your final monitoring progress. You're going to be asked to do several of these, so make sure that you can do them on your own before you start working on your homeworks. So let's look at our learning targets. First, we were able to identify similar triangles, and the best way to do this is to draw them all out facing the same way so we know which parts correspond in each triangle. Then we used several different real-life problems looking at those similar triangles, and then we were able to use our geometric means. Now you want to make sure and have these geometric means in your notes as you'll be using them often. So now I want you to go ahead and work on your homework for 9.3.